Alright, so in today's video we'll be doing something pretty similar to the one that we did in last video. So basically we want to still try to translate math into the language of logical statements, but we want to be more specific here. We want to deal specifically with sets. We want to know how we can translate sets into logical statements. So sets into logical statements. Now, I'm sure most of you have heard of sets before. If so, then feel free to skip about the first half of this video because we'll be mostly repeating things that you most probably already know and you don't want to listen to the same thing all over again. Uh, but for those of you who haven't heard about sets, let's continue. So what is a set? A set is basically a group of mathematical objects, and the way we write it is we place these mathematical objects within a bracket like this. So we put mathematical objects inside of this bracket. So we can put, well, the easiest example is basically just numbers. So we have 1, 2, 3, and so on, and this turns into the set of all positive numbers. And we can continue. Let's start with more examples, like let's say the set of all shapes. So it doesn't have to be numbers, it can be any mathematical object, as I said, anything you can think of. Shapes, matrices, vectors, tensors, I don't know anything at all. And we can continue on like that. So these are examples of sets. But this is not the way we actually write it. This is more of an informal way of writing things. The problem with this way is it's very ambiguous. Like, take this one for example. It's ambiguous because we don't really know if this is talking about the set of all 2D shapes, because it seems like we have a square, a triangle, and a circle, but it could also include a cube, or a cone, or a sphere. And we don't really know, we can't really tell. We just have these dots, which I don't know what it means. We don't know what it means. Nobody's telling us what it means. It could be a bunch of other 2D shapes. In that case, it will be the set of all 2D objects. Or it could contain cubes and cones, and then in which case it will be the set of all 2D shapes and 3D shapes as well. So we don't really know. It's not giving us a lot of information. That is why the mathematical community have decided to write things in a much better, more informative way. So the way they do that is you have brackets, same like before, and we place an X over here. I'll tell you what that means later. And we have a bar, a vertical bar, and we have basically what's after the bar is a statement that must be satisfied. Like, for example, X is even. That is an example of a statement that should be satisfied. So basically, this set contains everything that is even, because this is the statement that we're dealing with. Everything that is in this set must be even. So how do we actually read this set? How do we translate this set to English? Well, you can think of the bar here as such that it basically translates to these two words. So we have X such that X is even. So if we translate the entire thing, we'll have the set, which is denoted by these brackets here, which contains X because X is within these brackets, but we want X such that X is even. And I know it seems like a mouthful, and you won't instantly get it, but you'll get used to it very quickly. I wanna uh, elaborate on what X means. X here is basically a different way of saying any mathematical object. So what I mean by that is we can have another set at the top here, and I can write any mathematical object such that that object is even, and there will be no difference at all between the set at the top and the set at the bottom. Both of them will contain objects which are even, so both of them will contain 2, 4, 6, 8, and so on, and they are equivalent in that way. So basically, X just translates to any mathematical object. It's not like God told us that X should stand for any mathematical object, really. There's no absolute reason for it. We just do it because it's efficient and it saves time and it's just a lazy way of writing things. More compact, you know? It's just has a lot of benefits to writing the set in the bottom way rather than in the top way. It's really messy at the top. We don't like it, so we choose the bottom one instead, and that's all there is to it. But the downside is it introduces confusion because people usually think of X as an actual variable, that it stands for an actual number, but it doesn't. X literally means an English sentence that says any mathematical object. So it's not an actual number that you can play around with. It's a literal English sentence. Now, what more do we need to know about sets? Well, what if I write y over here and I add this fancy little symbol? Well, first, what does this symbol mean? It means element of or part of. So if we try to translate this entire statement over here into English, we'll have y is part of the set which contains a mathematical object such that those mathematical objects are even, and that's it, okay? So y is part of the set. The set is a set of mathematical objects which are even, so let's try to draw that out for visualization purposes, and so on. So somewhere along the lines, y is there, which means that it is an actual number. Maybe it's 10, maybe it's 12, maybe it's 100, who knows, but it is inside of the set, and the set is basically all numbers which are even, so we know that y is an actual number. Furthermore, we know that y is even. So y is an actual number. It has the property of being even, so it must be a number, you know? And so, yeah, you can notice the difference between y and between x. This is an actual English sentence that we just compacted into a single letter, while this is an actual number that we can play around with and put inside of an equation. So some people decide to put x into an equation because they don't understand that x is a literal sentence, and it just doesn't work. You can't put a sentence inside of an equation. So yeah, that's just something that you should be aware of. Alright, so we know about sets. How can we connect that with what we know about logical statements? Well, it's actually pretty easy and straightforward. Let me have, let me invent a symbol E, and I want to assign a meaning to E. I want the meaning of E to be even, okay? And I want to be able to attach brackets to E just like we did in the last video. And I want to put y within those brackets. So what does this mean overall? Well, based on the meaning that I assigned to this symbol, it means that y should be even. Now, isn't that similar to the top one over here? So yeah, it's pretty straightforward. They literally mean the same thing. Top one means y is even, bottom one means y is even. It's just that the bottom one, we're more used to putting that inside of a logic table and performing logical operations within it. And yeah, it's just helpful to know that we can move back and forth between sets and between logical statements, and it helps us realize that we can use logic, because if you have a problem in set theory or something like that, you're not entirely sure what to do, you can remember, oh, I can just use logical statements and continue on the problem that way. I just have to invent a symbol and give it the same meaning as the set at the top over here. That way, these two convey the same information. But the advantage is I can use this thing at the bottom here in the truth table and just perform logical statements. Now, final note here before we actually stop. We can actually simplify this, because this over here means y is even, right? So what if we change this thing over here and write ex instead? Then we have changed nothing, right? Because this means x is even, and the word that we just replaced is x is even. So literally we didn't change anything. So these statements should still be equivalent to one another. And it turns out, if you think for a little while, that it doesn't matter what E stands for, this at the top here will always be true to this at the bottom here. So let's test it out. Maybe let's give E a new meaning. Let's make E stand for the condition of being prime. So let's maybe rewrite this somewhere else. So y is an element. So this is the same thing as saying y is an element of x, such that x is prime, because we gave it a new meaning. And let's see if it still works. So this should be the same as y is prime, right? So E in this case means prime now. And is the bottom one and the top one true? Well, certainly, because y being part of this set over here means that y is prime, because it is part of the set of all prime numbers, whereas the bottom statement tells us that y is prime, because that's literally what this statement means. So this is a good thing. We figure out that the actual meaning of the symbol here doesn't really matter. It could mean even, it could mean prime, it doesn't matter. This thing at the top will always be equivalent to this thing at the bottom. And it's a great thing to keep that in mind as we continue on with this video series. Thanks for watching.